Hello, my name is Morteza Kayyalha, and I'm an assistant professor in the electrical engineering department at Penn State University. Today, I will tell you about our effort in trying to reproduce chiral Majorana modes in quantum anomalous insulated superconductor hybrid systems. So this work was done when I was a postdoc in Chuju Chang's group. So a great thank you goes to Chuju, Nitin, and Moses, who supervised the research, and my colleagues Dee and Roshi, who actually helped me with some of the device fab and measurements. So before I start talking about chiral Majorana modes, let me just briefly introduce you to quantum anomalous effect. So quantum anomalous effect is a zero field manifestation of quantum Hall effect. The most known material system that exhibits quantum anomalous Hall effect is magnetically doped topological inserts. So in these systems, depending on the magnetization direction, you get a clockwise or counterclockwise chiral edge mode. And the experimental signature for these chiral edge modes are if you do a normal Hall measurements, measure the longitudinal and Hall resistances. In the Hall resistance, you will see a quantized value accompanied by a vanishing longitudinal resistance, and this quantized Hall resistance actually changes sign when the magnetization is reversed. And this was observed experimentally by Chuju Chang and colleagues in 2013. But around 2010, there was a theoretical proposal suggesting that if you combine a quantum anomalous insulator with a superconductor, then what happens is that these chiral edge modes split into two chiral Majorana modes. So these are called chiral because they have the same chirality. They're traversing on the edge. So they're different than Majorana zero mode, which are localized. So the idea here was during the magnetization reversal of a quantum anomalous insulator, these Majorana modes, which you have two of them on each edge, will split, and then eventually you may end up with having only one chiral Majorana mode at each edge of this quantum anomalous insulated superconductor hybrid system. So in 2017, a group from UCLA reported the observation of these Majorana modes. And the sample that they had was a magnetically doped topological insulator. This was a millimeter size sample, and they had a millimeter size niobium deposited on top of it. So let's take a quick look at what they have, what they had reported at the time. So I need to mention that this paper was recently retracted by an editorial retraction. So nevertheless, we're just going to look at what they had reported here. So in a quantum anomalous sample as the one that is shown here with a niobium superconductor, the width of the superconductor is 0.8 millimeter deposited on top of it. They saw that if you are in a well magnetized region where the magnetization is either up or down, then consistent with the theory, you have two chiral Majorana edge modes, but the effective result is that you will observe a quantized value of the conductance if you look at the two terminal conductance measured across this superconducting strip. Interestingly, however, they observed that during the magnetization reversal, you can see a half quantized conductance. And they interpreted this half quantized conductance as the evidence for the chiral Majorana mode. And the schematic here kind of like shows what's happening in the sample. So there you have the superconductor, you get only one chiral Majorana on each edge of the sample. And then the other chiral Majorana that exists inside the quantum anomalous insulator will kind of be reflected from one edge to the other edge. So this effectively will give you a half quantized value. I note here that if this picture is true, actually this value of half quantized conductance would not depend on the number of superconductor strip that you put here. So if you increase the superconducting strip from 1 to 2 to 3 to 4, it does not impact the quantization here. You should always see a half quantized conductance. Anyway, so they interpreted this half quantized conductance as evidence for chiral Majorana. And then they also observed that when you enter at the insulating phase of the quantum anomalous insulator, nothing is happening. You have an insulator, nothing is going on. There is no current or almost no current. So after this paper was published, I joined Chuju's group and I kind of like set out to reproduce this data. So in my early attempts, I didn't want to use any lithography because the experimental report in that paper seemed to be actually done on millimeter size samples. So there is no lithography needed. So I got a bunch of quantum anomalous samples. This is basically 6 quantuple layer chromium doped bismuth antimony telluride samples. And then I did a bunch of sanity checks. So first I looked at the Hall and longitudinal resistance of this sample. I saw that the Hall resistance was quantized, longitudinal resistance was vanishing. So I concluded that, okay, I have a relatively good quantum anomalous Hall sample. Then I deposited a niobium strip on top of these samples. And then I looked at the 2 terminal conductance measured between terminal 1 and 2 here. However, what I observed was that this 2 terminal conductance is always almost half quantized. So this was measured in a bunch of samples in millimeter size samples. And then I also tested the theory that if you have more than one superconductor, if this half quantization is caused by the chiral Majorana mode, then it doesn't matter, you should still see half quantization. But what I saw in the experiment was if I increase the number of superconducting strips from 1 to 2, instead of seeing a half quantized value, I see 1/3. So the sample is now quantized, but 1/3 of E square over H. So then I decided to actually design a more systematic sample so I can study everything in one device and actually get a better understanding of what's going on. So I made these samples. This is done with lithography. So I used the e-beam lithography here. So this sample actually serves a bunch of different purposes. So first, I have a normal Hall bar, which allows me to check the quality of the sample. I have a superconducting strip. The width of this strip is 20 micrometer. And this would allow me to measure the 2 terminal conductance. And as you can see, I have a 4 terminal, like normal gold contacts here. So that would allow me to exclude any contact resistance from the wires in the dilution fridge. So I can actually look closely at the exact value of the quantization here. And then I also made a niobium finger, which is around 200 nanometer wide. The reason that I'm using a finger here is because this finger geometry allows me to actually look into the interface between the superconductor and quantum anomalous. So this is not the best way to do the experiment. Perhaps you want to make a Josephson junction or do tunneling spectroscopy, but this is good enough to just see whether the superconductor is contacting quantum anomalous or not. So now, after I made this device, I did a bunch of sanity checks. So the first sanity check was, I have niobium, is it superconducting? So I looked at the niobium strip and niobium finger. The niobium strip is wider, so the TC is around 8.5, BC is around 2.9. Niobium finger is much narrower, so the TC drops to around 5, BC drops to around 1 Tesla. So conclusion here is my niobium is superconducting. Then the next sanity check was, okay, do I have quantum anomalous insulator here? So I looked at the Hall bar that I had, and I see a quantized Hall resistance and vanishing longitudinal resistance when I measure the Hall bar. Then I looked into the two terminal conductance across the niobium strip. And what I see here again is that this two terminal conductance is always half quantized. The only time that is not half quantized is during the magnetization reversal. And I can actually look more closely at this transition. And what I see is that there is nothing strange is going on. It's just the resistance becomes larger, conductance becomes smaller due to the transition, and then it recovers the half quantized value. So then I ask myself, okay, I have always this half quantized value. What is going on? Let's take a look at the, actually, there was another reason that this science paper, the 2017 science paper by the UCLA mentioned is crucial for the observation of Majorana, and that was the emergence of this C equal to 0 insulating phase. So in order to actually look into that, we also grew some samples that show a very well-established insulating state during the transition. So these are, we call them axion insulators. So they're like chromium doped and vanadium doped samples kind of like stacked together. So if you look at the normal Hall measurements, the Hall conductance is quantized and then it becomes insulating. So the Hall conductance becomes 0, and then it changes sign and becomes quantized on the other side. And then the longitudinal conductance is 0 everywhere except during these transitions. So we have a very well established 0 Chen insulator here. And then I made niobium contacts on top of them and then measured the two terminal conductance across these samples as well. And then I saw that the conductance, regardless of whether you have this insulating C Chen insulator 0 or not, is always half quantized. So that really does not play any role in this half quantized conductance value. So then I wanted to actually look into the interface between the niobium and the quantum anomalous Hall insulator. So I use this niobium finger again. The reason I'm using this finger is because the superconductivity is weaker there. So I can actually study some Andreeff reflection processes here. So here I'm looking at the excuse me. I'm looking at the conductance, two terminal conductance between the niobium finger and the magnetic TI. And I'm kind of like sweeping the current that I'm injecting through this finger to the magnetic TI. What I see here is that below a certain value of the current, there is a jump in the conductance. So I associate this jump to the observation of some sort of Andreeff reflection. The reason this is very sharp is because, again, these are not tunneling measurements. So the niobium finger transitions from superconducting to insulating state. And that's why these jumps are very sharp. But the resistance value that we see here is actually very large. So the change in the resistance is several kilo ohms, whereas the niobium finger resistance is several or hundreds of ohms. So this change in the resistance cannot be due to the transition or superconducting to normal transition of the niobium figure. It has to come from the interface because it is much larger. So we see around like 80% enhancement in the zero bias conductance. So we know that there are some sort of Andreeff reflection going on in these samples. So the superconductor not only is superconducting, but it's providing relatively good contact to the quantum anomalous Hall insulator. And in order to do another sanity check, make sure these are actually Andreeff reflection, is if you increase the temperature of the niobium above the niobium critical temperature, then you see a flat line. So no enhancement in the conductance is observed for these samples above the critical temperature of niobium finger. So that indicates that whatever we are seeing here is caused by the superconducting state in the niobium finger. So then what is going on? We have a superconductor, we have a strip, we put it on top of quantum anomalous Hall insulator. We always have quantized conductance if we have one strip. If we increase the number of strips to 2, then we see 1/3. If we increase it to 4, then the value of the quantized conductance just keeps dropping and dropping. And then we have also confirmed that the niobium finger provides, or the superconducting contacts, niobium in this case, provides relatively good contacts to the quantum anomalous Hall insulator. So there is no insulating barrier in between as far as we can tell. So what is going on? And the effect is actually relatively straightforward. It has been observed multiple times in the past in quantum Hall systems. And the idea is kind of like schematically shown here. So when you have these millimeter size superconductors, so this green strip here is my superconductor, and then you put it on top of a quantum anomalous Hall insulator. What happens is that this chiral edge mode of the quantum anomalous Hall undergoes Andreeff reflection under this superconductor. So depending on the skipping orbital of the quantum anomalous Hall, we believe this is around tens of nanometer. So this, for a millimeter size sample, it happens, I don't know, many times. So as this Andreeff reflection keeps happening, because of the chirality of the system, the electron and holes that are coming out of this Andreeff reflection process that have the same chirality. Again, this is also a very known fact in quantum Hall insulator and chiral edge modes. They keep their chirality regardless of whether electron or hole is coming out. So as a result of these multiple Andreeff reflection, what happens is that eventually you get this incoherent superposition of electron and holes, or you can call them pair of Majorana modes, does not matter. But the interesting point is, after many Andreeff reflection, it's kind of like multiple Andreeff reflection that is happening here, you will have an electron injected into the superconductor. And this happens on the both side or both edges of the superconductor or the quantum anomalous Hall insulated sample. So these two electrons provide an electrical short between the two Majorana modes. And once we measure the resistance or two-terminal conductance, we are basically measuring two quantum anomalous Hall in series. So we get half quantized value. If we have two superconducting strips on top, then we are measuring 3 quantum anomalous Hall insulator in series. So we get 1/3. If we put 3 niobium strips on top or superconducting strips on top, then we have 4 quantum anomalous Hall insulators in series. We get 1/4 E²/h. So this is just simply an electrical short. There are some other alternative explanation provided in this physical review letters and physical review B relating to the disorder effect and then equilibrium between the two edges. But at the end of the day, both of these theoretical work suggest that because of these effects, you have this kind of like strong coupling between the two edges that creates the half quantized value. So that's why we don't think this half quantization is an evidence for chiral Majorana mode. And just to conclude and give you an outlook of what I think personally we need to do in this field in order to be able to study chiral Majorana mode. Before even talking about any Majorana, we should show a few basic things. So first is reduce the size of quantum anomalous Hall insulator to the range where talking about coherent superposition of electron and holes or chiral Majorana modes is relevant. So this is already achieved. You can see an example from Juju Chang's recent work on these samples in PRL. I believe they obtained quantum anomalous Hall with width around 72 nanometer or so. The next step is make transparent contacts to magnetic TIs or topological or quantum anomalous insulators. And you can actually do this or confirm this by doing tunneling spectroscopy or making Josephson junction show that there is a supercurrent flowing between two superconductors when you have a magnetic TI in between. So do the basic characterizations, then show that you can actually induce superconductivity in the chiral edge mode. So these are things that have not been experimentally observed. So can we induce superconductivity in the chiral edge mode? What is the impact of disordered Bach? Do they also carry any supercurrent, or is the entire superconducting state is carried by the chiral edge mode? What is the coherent length of the bulk? What is the coherent length of the edge modes? Can we observe any interference between the chiral, I would call them chiral and rift edge modes, or whatever this induced superconductivity in the chiral edge modes is called? So can we do some interference measurement there? So once we do all of these things, then I think we are ready. We are at a stage that we can start designing experiments that can look into the existence of chiral Majoranas. But just to give you a little bit of perspective, I think doing these basic experiments in quantum anomalous insulated superconductor system is interesting. I think this is a very exciting research direction. And you can envision multiple applications beyond just chiral Majoranas. Having induced superconductivity in a chiral edge mode of a quantum anomalous insulator, because of the symmetries that are broken in the system, time reversal symmetry is broken, inversion symmetry may be broken. You can create novel superconducting state, whether there is Majorana or not. That's beside the point. I hope that the controversies that have happened around this field do not dissuade the community, especially the funding agency, from funding more research in this direction. I haven't had that good experience with the funding agency. Unfortunately, when you talk about chiral Majorana, then they usually shoot you down. But I'm hoping that through these workshops, the message is kind of like delivered to the community that this is still a very interesting field, and there are lots of things that we can do. Anyway, thank you for your attention.